Thank you so much. Thank you for the introduction, but most of all, thank you for such an enlightening talk, especially for someone like me who's absolutely not a subject matter expert. I learned a few things today. Thank you very much for having us here as well. So I wanted to personalize a bit this story, this discussion, having read your book, and if you haven't read this, it's absolutely worth a read. You've been chasing gravity throughout your entire life. And I wonder if you could talk a little bit of how you developed the fascination with gravity at such a young age, when you did.
Thank you. That's such an interesting question. And I don't know if it's something that I have developed or I have simply not lost. I think some of this passion, I really want to believe that it's in all of us from an early age, and I can see that we're all fascinated to some level with that phenomenon. And it's about not giving it up. It's about keep playing with it. There's some element from a scientific level where we understand how universal it is, and it is so profound that to me, experiencing it is something you can't ever give up. But on a more human level, I think we are all teasing with gravity to some extent. The notion of gravity, the notion of challenging gravity, and how we play with motion for gravity. I think you can see in the Olympics, for instance, almost every sport is a little bit of a teasing with gravity to some extent. So perhaps there's a level of the child in me that has never given it up. But it is also, I think, this fascination for gravity and this scientific perspective is part of trying to be part of something bigger than us. There's something quite fundamental about that, about gravity itself, about the structure of space-time, even though that's probably not the way I would have phrased it from an early age, but very much in trying to understand the whole of the universe around ourselves, being part of something where you can feel you can understand, you can appreciate. So it very much started with that.
Yeah. One thing you've done since an early age is travel. You've lived in so many different countries. I'm curious, and stop me if this is overstating things, whether you thinking about gravity and, contemplating gravity has in some way kind of kept you grounded, both literally and metaphorically.
Absolutely. I think understanding how you're being part of this bigger structure was very important to me. If you have to move from one place to another, you want to attach yourself to something which is more profound. And perhaps I wouldn't have phrased it myself as a child as gravity per se, but very much into understanding our whole surroundings, understanding nature around us, understanding the cosmos. I think there was very much this notion that things change all the time, and there's a level of chaos around us all the time. But the sky itself doesn't change, and there's some constants in nature that you can attach yourself to, that you can always go back into. And that is related to astronomy, it's related to cosmology. I think it's related to nature as well, but it's also related to this scientific stability. If you can rely on science to keep you grounded, it's much more peaceful, and it was a way for me to make sense of everything around me.
Yeah. Now, falling is such a central part of your book. It's part of the title. It's a paradox in a way because it's caused by gravity, but yet we don't know what weightlessness feels like, as you mentioned.
Yes.
I'm wondering what it is that made it so compelling for you, this idea of contemplating the feeling of weightlessness.
I think there's an element which is blissfulness in some level. You extract yourself from any other type of distraction. Everything else is a distraction. Falling in itself is actually very, very beautiful, and we may not have this impression because of what happens after the fall itself,
right?
Which unfortunately on Earth we can't really evade. Yeah. But in itself, that's not the fault of gravity. It's very much giving yourself completely to one of the most natural phenomenon, and I think we all like that to some extent. Perhaps I don't have a survival instinct which is as strongly developed as other people, so maybe a mind less, just letting myself go and experimenting this.
We all like the idea of it, but you went to great lengths to experience weightlessness. Can you talk about some of the endeavors that you've undertaken besides falling?
and hitting the ground, which I've done a lot. And that's part of it as well. So I mean, one of the experiences that we can all do, which I loved, is simply swimming and actually experiencing some level of buoyancy in water. And I started scuba diving from a very, very young age. And it wasn't the sport in itself, it was very much the feeling of being part of this environment and being able to contemplate it in complete peacefulness, really being completely part of it as opposed to observing it from an external point of view. To me, that was very important to be immersed in those elements. And there's something quite surreal about it, where you can completely disconnect from the reality in which you live in once you are in those environments. It's the same thing with flying, actually. When I was a postdoc here, a few years ago now, I started to learn to fly, and that's probably one of the most thrilling experiences you can imagine. It's being part now of the sky, and of course there's lots of things to tackle, and lots of your brain is quite busy when you fly, but it is very much in letting yourself to those elements as well and playing with them to some extent.
Yeah. And all of these pieces, all these actions were leading to a very dramatic moment in your life, which is when you were very close to being chosen as an astronaut.
That's right. Yes, so it is very much, I can't even say which one came first to some extent, this driver to experiencing things and being part of other elements that pushed me also to wanting, like many other people, wanting to become an astronaut. Right. And it's rather than just being a dream and then something that slowly faded away when reality hit me. It never really faded away. For years, for decades, for more than 2 decades, I had this constant dream that I would want to become an astronaut.
And you came really close.
And I came very close.
8,000 applicants to become an astronaut for the European Space Agency. You were one of the last 40. Can you talk about what you had to prove? What is it that you had to do to get to that level?
So there's many different stages. I should say that the application process, I was for the European Space Agency, because I'm European. I was at the time. It happens every 15, 20 years, so you can't try again. It was a once-in-a-lifetime opportunity. So many people are excited by the idea. Many people try out. More than 10,000 people started the process at the same time as me when it opened up. And so you go through various selection processes, through some simpler, I would say, medical screening and sort of different screening, which was computer-based, but then you had much more intense psychological and team bonding, sociological screening, which it's hard for me to even say what it is that they were after or not after. It's interesting, but what I can say is that as the process went along, we ended up with smaller and smaller groups, and really the connection with those people was very profound. You could imagine yourself being locked in a very small room with them, and it would be fine. You could be in an emergency situation, and it would be fine. And throughout the latest steps of the process, it was a week-long medical screening. In that case, it was in Toulouse. We were 7 of us, really almost locked down in that medical facilities with all sorts of medical tests that you can imagine. And it's not like our life was threatened. It's not like it would have been different if we had real medical condition. But still, it was pretty intense. We had to go through one test after another. And rather than feeling any sort of competitions with one another, there was very much this sense of bonding, and we were in it together. Mm-hmm. It was a very fulfilling experience.
Yeah, a fulfilling experience, but also one that left you disappointed.
I guess falling. When you hit the ground, that's part of it.
It was a technicality in the end.
Pardon?
It was effectively a technicality that prevented you.
So it was something I couldn't have done anything for, I think that's fair to say. It was sort of funny to some level, maybe not so funny, but I went through all of those tests, and the last day, the medical doctor in charge and I had a meeting going through all of the tests I had gone that week. And he said, oh, there's just one last test we haven't had the results for. It's TB, tuberculosis. And I thought, okay, we can wait for that test if you want to, but surely I don't have TB. I'm not coughing. I'm fine, right? I think. And I had been tested against TB in the past, and it always came up negative. So I thought that was fine. A new test had come along. It was called the QT test, and it was much more sensitive. And it turned out I was positive for it. I had latent TB, it turned out. So you've been infected in your past by TB. So you have the antibodies for that, but I never really declared it, and so I didn't actually know that I had it, and that was it. That was really it. So yeah, it was a bit of a disappointment. I think that's fair to say.
A disappointment, but you took away a lot from that process. What was your biggest takeaway from going through that process?
I think it's very much the persistence. It's not about the end at the end of the day. It's very much about the journey and about all the things that you learn to go into it, knowing that it probably won't work out and you still do it anyways. And I think this is something in the scientific process, in the research that I do in my everyday life, it's very much part of it as well. We do research, we look at models, we explore ideas, knowing very well they probably won't work, but that doesn't matter. It is part of the endeavor. It is part of, I think it is a very human quality in itself that we take the chances, we take risk in how we explore everything around us, and that's how allowed us to be where we are and reach to that level. Otherwise, we would just be doing the things that we know we can do very well, but not going beyond that.
In your book, you write that we are creatures of gravity. What does that mean?
I think there is this connection, which I think is at every level with gravity. There's an element which gravity is this attractive phenomenon, and we are the result, we are the fruits of those attraction. We are part of it in a way that we can never really escape, which I think it is part of this wanting to challenge it to some level, but at the same time, we know very well we'll never be able to escape gravity. It's there all along because it is part of space-time, it is part of the way we are thinking, it is part of everything that we are.
So can we go to the beginning, to that point that you described both visually and orally, the beginning, the Big Bang, and talk about where gravity begins in that moment? Is it exactly that moment? Did it come afterwards? Do we know?
We don't know. Even when we reach those levels, the very notion of that moment in time, stops making sense because gravity itself is intertwined with the notion of space and time, and gravity stops making sense at the Big Bang. So the very notion of time itself may stop making sense. And if there's such a thing as before the Big Bang, I don't even know that I can necessarily formulate that question. Some of my colleagues think they can. I don't know myself. I don't know. Where does space and time come from, and how they started to realize is one of the biggest mysteries there is. And a lot of research that is actually being done in here, that is being done in my home institution, is driven precisely by those questions of how to even phrase the notion of space and time or the notion of gravity when the standard the standard tools that we're using to describe them stop making sense.
I want to expand a little bit on a point that you talked about that is well beyond my comprehension. And so I'll ask it very simply. If gravity were any different than what we know and experience on a daily basis, even by the tiniest amount, how different would the universe be? In what way would it be different?
So we do rely very much on this interplay between the strength of gravity, the behavior of gravity, and everything we're living in it. And we understand how we are where we are in terms of living in a cluster of galaxies that got just form from having the right condition and having the right evolution of the universe throughout its billions of years of existence. And if gravity had been ever so slightly different, all of this, the way the galaxies would have got formed, the clustering of dark matter would have been very, very different. Right. And so we are very dependent on these very subtle effects on gravity.
You say that it's essential to the integrity and the structure of the universe, but you also say that it's weaker as a force than other fundamental forces. How much weaker, and what does that mean?
Yeah, that's an excellent question. How much weaker? And it's hard for us to think of gravity being weak when this is really what we're experiencing. Yeah. Maybe to give you an example of how weak gravity is. You imagine we are actually experiencing the whole gravitational pull of the Earth. Can you imagine just how big the Earth is? And all of the mass of the Earth has a gravitational pull on us. Now, I can take a simple party balloon and rub it in my hair and pulling out. What will have happened then is just a few electrons from my hair will have been transmitted to the balloon. And there will be also, in addition to gravity pulling my hair down, there will be this electrostatic phenomenon that pulls my hair up. And it will win. Just a few electrons that have been transferred between my hair and the balloon are sufficient to counteract the whole phenomenon of the Earth. This is incredible. And so we don't think of it like that in everyday life because we are very much grounded on the Earth. But in some level, at the smallest other level of other fundamental force is much stronger than the gravitational force.
Staying in the past a little bit, can you talk about what you know as the earliest idea or theory about gravity pre-Newton? I mean, I have not heard of any theories that predate, that are, early times. Do you know of any?
So one of the beauty with Newton, it was very much to understand, to formulate it mathematically, yeah, and to understand that it is universal in the sense that what we are experiencing here and what we're experiencing in the solar system, in the way the motion of the bodies in the solar system, it is the same phenomenon. And so, and that Kepler himself was also exploring. Mm-hmm. But I think a lot of the predecessor would probably separate many of these phenomena in how we're experiencing the strength of gravity here on Earth and what is out there, which seems to be too puzzling to being explainable in simple terms. Yeah. So I'm not answering your question. It was very much in this unification of both ideas that Newton made a huge leap forward. Yeah.
Apologies if this is such a basic question, but again, it seems every time I read about gravity, there's no escaping Einstein. Is there a sense in which, when you talk about gravity, all roads lead back to Einstein?
There's a lot of things that we have that humanity has discovered in the past century, which goes back to Einstein. But the reality is he came up with those ideas not by himself out of the blue. Those were bubbling in at the time, and it's very much us as human, as the community at the time, being ready at the scientific level to come up with those ideas. So it was only possible because of the developments of other people, like Lorentz, like Minkowski. All of those notions were just on the edge of being developed so that Einstein could put them together and come up with Einstein's theory of general relativity.
Isaac Newton wrote, just to your point, if I have seen further, it is by standing on the shoulders of giants. And your work and the work of Einstein and others who have worked in this field builds on Galileo, Newton, Einstein, of course, Stephen Hawking, and many others. But the process of how this work is done is very much shoulder to shoulder. Can you talk a little bit about that process, what it takes to actually advance the science of gravity, how you come up with a new idea, and what the role of the rest of the community is in confirming or not confirming it?
So I think it is true. It's very much an endeavor for the whole community. And you can think of it almost as a sea where we have the whole community and there's bubbling in and out some different ideas. And some of those ideas will ultimately make sense. Some of those ideas were proposed way before their time. and the community itself wasn't ready to accept it or to think of it in these ways. So it's very much an emergent phenomenon in how we make advances, in how we understand things, and how, I think I was talking a little bit in how we have the tools to express it. Yeah. Sometimes some of those ideas are correct and have been present, but expressing it in a way that the whole scientific community can actually make sense of it and accept it and move forward from that, actually do something with it is very important. But I think there is this level of creativity. There's an art in itself where you need to draw a slightly different picture in slightly different colors, but you can't do that if the framework is not there to some extent.
Mm-hmm. So back to Einstein, is it fair to say that you're always dealing with Einstein's theories, either pushing against them or proving them or disprove them?
I think it is true. I think maybe I should say even in the way we think about, let me just say gravity, but I think that's true for physics and even science in general. It is not quite the case that Newton came up with a theory of gravity and that was wrong, and along came Einstein and rephrased it in a way which was correct. It's not quite like that. A lot of the concepts of even Newton, we're still using them today. There's a lot of beauty in Newton's description of gravity, which is used in Einstein. So it's not binary, it's not right or wrong, and then we move like that. It's very much into going deeper and deeper in our understanding of science. It's layer after layer, and it doesn't make a previous layer incorrect per se. It's simply not the full description, and so you want to go in deeper and deeper details in how we describe it. But definitely Einstein's understanding of gravity, among many other things, is doing such a beautiful job at describing, I would say, everything that we understand about gravity and the whole variety of scales, that there is an element of scientific truth in it that we can't disconnect ourselves from. We can't simply say, let's give away with that and come up with something completely new.
Yeah. You talked about this a little bit earlier, and I think a lot of people like me would have trouble getting their heads around this, but can you explain again how gravity is not just the effect of the curvature of space, that actually it's entwined with space and time? Can you just give us a simple description of how that happens?
Yes, so I think one way to think of it is...
in 1 minute or less. Joking. No, please take your time.
Okay. Thank you. Thanks, time is relative. So I cannot play that to my advantage. I like to think of gravity almost as the life of space and time. You can think of the space-time as almost a caveat, the bare painting that gives you the framework, but gravity is actually what brings it to life, what actually brings the colors to it. Something to think about gravity is that even though you can think of it as the way we are experiencing it through the manifestation of the curvature of space-time, there's much more of an interplay there than just being something static. It's not just the mass gives rise to curvature, and therefore we're experiencing it, sitting on it. It's very much of a game between us living on our space-time, affecting the space-time ourselves, and then feeling the effect of that. So it is a two-way process. Maybe related to that as well, it is not just the fact that gravity is simply the manifestation of the curvature of space-time, and we have to give way of the notion of force from gravity. Those notions from Newton themselves and people before him has still some level of being correct to some level. And there is this notion of force embedded in gravity itself that we have experienced. We have experienced the force of gravity through the detection of gravitational waves. This is this distortion of space and time that is happening, and that is a manifestation of gravity through a force in itself.
So is it fair to say that we don't so much live with gravity as opposed to living in gravity? Is that a more accurate way of describing it?
We are living in gravity, and we affect gravity as well. So it's very much of a collaboration with gravity. In gravity, we are embedded in that, and I think it's part of the creativity of gravity. Yeah.
One of the things that was predicted by general relativity was black holes. And even though Einstein himself didn't believe that they actually existed, what happens with gravity, with the curvature of space-time in a black hole?
Okay, so already when we go close to a black hole, the gravitational pull gets very, very intense, to the point, as probably you know, as you get close enough to the horizon of a black hole, you can no longer escape. So you can try to run away from it as fast as you can, but you wouldn't be able to escape it. Now, as you enter the horizon of a black hole, first, the very notion of space and time, because they're intermingled, they sort of interchange each other. So when you think of the notion of where is the center of a black hole, that even notion doesn't make sense because it's not a position in space, it's a position in time. So in the sense that you can't avoid the flow of time, as you enter the black hole, you can't avoid the flow which pull you towards the center of the black hole. And so we inexorably being pulled towards the center of the black hole. As you do so, the curvature of the environment in which you are becomes higher and higher. And this, even though we can't go inside a black hole and actually measure that and experience that, we do think that the laws of gravity, the laws of Einstein's theory of general relativity still make sense. We have no reason to believe that actually would be violated as you enter the black hole. And we actually have experienced gravity in curvature region which are just as strong as what would happen as you enter inside the black hole. And so we have strong reasons to believe that we can trust it, and the prediction of Einstein's theory of general relativity do tell us that then the curvature becomes larger and larger and larger as you reach the center of the black hole, up to the point where the curvature becomes so large that we can't make sense of gravity as described by Einstein's theory of general relativity anymore. And so to me, it's kind of remarkable to see that Einstein's theory of general relativity in a regime where we can trust it predicts that it will enter a regime where we can no longer trust it. Mm-hmm. So Einstein's theory of general relativity to some extent predicts its own failure.
Right. Which makes it very special indeed.
It makes it very special, and I think to me this is really a huge quality for a theory. It's not something to be looked down on, because if you know that a theory, if it predicts from the outset when it will break down, you know from the outset where to look for new physics. It is something very much to be appreciated.
Yeah. You, of course, talk about beyond all of this and say that the story of gravity goes beyond the curvature of space and time. And you talk about something called Glight or Glight. Can you just explain what that is?
Yeah, so Glight or Glight, however you want. It's a made-up term, but I like it because it draws very much the analogy between light, which we all experience, and it's something not extravagant in any way, and gravitational waves. And we're all experiencing light. It is actually the manifestation of electromagnetic waves. Light are electromagnetic waves. They are fluctuation in the electromagnetic field. It is related to the electromagnetic phenomenon, and that's something we've detected for thousands of years, millions of years, and we know very much nowadays how to represent it, how to express it. And there's a direct analogy between that and gravity. So once again, we do put a lot of emphasis on gravity being very different from the other fundamental forces of nature, but to some extent there's many aspects of gravity which are very similar to the other fundamental forces of nature. And just like we know how if you have, let's say it's a stormy day, and there's a lot of electricity in the air, there's a quick discharge of electricity, a quick discharge of electrons. What happens is actually electrons get accelerated, and they produce lightning, they produce light. This is what we're experiencing when there's storms and when there's lightning. And the same phenomenon happens exactly for gravity. When you have, let me say, charges with respect to gravity, so let me think of them as masses, when they accelerate, for instance, just when I shake my hands, like that, when I shake my hands, I do produce some not lightning, but glightening. So the same phenomenon before gravity. Those are called gravitational waves, but actually, in analogy with light, we can call them Glight. They are actually very similar to that.
So we are all here sitting, emitting gravitational waves, is what you're saying?
Your heart is emitting tiny, tiny gravitational waves, Glight. We're not going to detect those. It's not that we don't have the instrument to detect them, it's that the amplitude of those is too weak to even be theoretically possible to detect them. But yes, this is happening.
And what evidence is there of their presence?
So we have very strong evidence now of Glight. We have detected Glight, not from your heart, I'm sorry, and not from us dancing with our partner, but we have detected Glight emitted by much more massive objects. And we need to have much more massive objects to see the effect of that, because gravity is such a weak phenomenon. And so rather than just being sufficient to have just a few electrons being accelerated to emit light and seeing that, we really need astronomical objects to be accelerated, and like two stars or two black holes, when they're accelerated very close to one another, then they emit gravitational waves, they emit light with sufficient amplitude that they're actually observable, and we have observed them. So the existence of what I call Glight, or what the existence of gravitational waves, now is not theoretical, they have been observed, they are reality.
And they're not instantaneous, however. Like if a black hole were to form, in space somewhere, it would take a long time for us to feel.
Yes, so the ones we have observed, they happened millions of years ago, and they've been traveling constantly through space at the speed of light until they reach us,
So this brings us to your own work on gravity, and your own theory of gravity, that it has mass. And you mentioned the graviton earlier, at least briefly. So I just want to understand. It's the particle in G-light, and it has mass.
So in my theory, in a theory that you can consider, it would have mass. In Einstein's theory of general relativity, Einstein himself predicted gravitational waves, let me call it Glight. Then he thought they didn't exist, but in the end, he predicted them, and they have been detected. Those gravitational waves, if we think of them at the classical level, they are phenomenon. But if we think of them as an analogy with light, we know, for instance, if we take light of a particular frequency and we reduce the intensity as much as we can, it's not a complete continuous spectrum of energy that can be carried by light of a particular frequency. It actually comes in discrete quanta of energy, which we can think of particles, and those are called photons. And these are reality in the sense that they have been observed. We know that light is actually a quantum phenomenon deep down. It's carried by particles which we call photons. And we know that, for instance, we can detect we can see that electrons, as they jump up and down the energy level around the atoms, they can absorb or emit single photons. Now, by direct analogy with that, we can think of Glight, which is a classical phenomenon. We can also embed it within a quantum framework, and that is not controversial. And so if we do that with Einstein's theory of general relativity already, nothing to do with mass or no mass, we would expect gravitational waves or Glight to also be carried by finite quanta of energy. And in that case, we call those gravitons. So gravitons are the particles living in gravitational waves. Now, the distinction between Einstein's theory of general relativity and other models of gravity that we may or may not want to consider, which could have a finite reach, would be the fundamental properties of this particle, of the graviton. So in Einstein's theory of general relativity, that fundamental particle is a massless particle, like the photon is in electromagnetism. It is a massless the photon is a massless particle. But people have been considered what the possibility would be for having the photon itself being a massive particles. And there are observational experimental constraints out there putting a constraint on the mass of the photon. This is something people are considering. And so you can think of the same thing for gravity. You can consider what the observational consequences of a graviton mass would be. So this is the type of theory that we are considering.
Yeah. At the risk of asking a question that maybe goes beyond the scope of the time that we have possible, I'm finding it hard to kind of get my head around how gravity can be the effect of curvature in space-time while also existing as a force and produce waves and be a particle that has mass. How is that possible?
There's many different manifestations of gravity, which I think makes it so powerful. I think in the way we think of it, the geometrical picture is extremely powerful to some extent, but again, I think there is a life to it which sort of goes beyond this geometrical picture and is very much encoded in this dynamics of gravitational waves, but also in this dynamics of gravitons, and tells you that at a more fundamental level, actually, there's nothing wrong with putting gravity at the same footing as the other fundamental forces of nature. And so gravity is a force deep down, like the other forces of nature.
Even if weaker.
Much, much weaker, yeah.
The other thing, other perhaps counterintuitive, at least to a non-subject matter expert, part of your theory is this idea that gravity is finite, that it ends if two things are too far apart. In the simplest terms that you can muster, how is that possible? How is it possible that gravity is finite?
Okay, so this is very much related to the notion of mass. So just to try to convince you that this is not completely crazy, which it may be, but that's okay, because I think we should explore things. There's a thin line between craziness and creativity sometimes. The finiteness of a force is something that does happen in nature. It does happen for some of the fundamental forces of nature, and that's why it is interesting and it is relevant to compare it with other phenomena in nature sometimes. So for instance, have you heard of the weak force?
I have not.
No, you haven't. No. You haven't heard of the weak force, and I wouldn't have expected, because the weak force is actually weak. And so we that's how deep I am.
Aptly named.
and so we don't really experience it in our everyday life, although it is extremely important for the structure within the atoms. It does go into the atomic structure. It is very important there. The weak force has some applications, so it's not something that just came up from my imagination. It's related to radioactivity, for instance, but we don't experience it at the same level as we're experiencing electromagnetism, because the particles that carry it, they are not called photons, they're called W and Z boson. They're actually massive particles, not in the sense that they are huge, but in the sense that they have a mass, and the existence of a mass affects their inertia, affects their dynamics. And so in that context, having a mass prevents your dynamics and prevents you from propagating very far. This is sort of a cartoon picture. It's not the complete picture, and it's not completely correct, but just to give you an indication of how to think of it. And so if you were limited in your motion, if you were limited in your ability to travel very far, that would limit your range of applicability. And this is actually what happens for the weak force. And we understand how that happens at the particle level, at the fundamental level. And so in this context, it is useful to think of it in the same way for gravity. When you think of what happens for gravity beyond the range of gravity, I think this is where your question comes in of how can I make sense of gravity if it is everything about space-time? How can I think of having it a finite range? And it's not that space-time itself stops making sense after the finite range of gravity. It's just that the gravitational interactions through the curvature of space-time are inhibited.
Or even just more basically, the fact that it's an attractive force suggests that it is always attractive. And I think of two magnets, but that's really simplistic, isn't it?
So it is always attractive. It's about how attractive it is and how it continues being attractive if you bring them very far away from one another.
Yeah.
And again, this picture is sort of simplistic because we think of it in terms of distance, but in everything we think, it's not so much about distance in space, it's encoded in space and time, and the notion are much deeper than just space and time themselves, but it's to give that perspective.
Let me go back to an idea you just raised a moment ago, this notion that this theory is crazy. Or
How can I regret that now?
it's not obviously the word that I would use or you would use, but it does go sort of in contrary to much conventional scientific thinking. And I wonder just if you could speak to what it's like to work so actively and persistently against the grain of scientific convention.
Challenging is probably the first word that comes to mind. So I think for me, but I think for every scientist like me, just being able to think of new ideas is just a gift in itself. I think it's really a privilege. And we very much know that sometimes those ideas will work out, sometimes those ideas will be also understood, and maybe they will be wrong for what, or not applicable for what we wanted them to do, but maybe they still have some inner structure in them, some inner beauty in them, which is applicable for something else, which is often the case. I think I mentioned that a little bit when I talked about, for me, going against what the standard consensus is, was very much in trying to understand, taking in how much it is about what you are developing not making sense in itself, and how much it is about connecting that with the way people are thinking. And I can tell you, I mean, I work on models which sometimes can be seen as being controversial. I do get a lot of feedback from people coming up with their own theories.
Sure.
And it's not as simple as that. It's not that we can just give away everything we know and just come up with something else out of the blue. We really need to embrace everything that we know, understand it even beyond any of the limits, so that we can understand how precise any little tweak will be. And I should say, if anything I'll learn about all of those explorations is how precious general relativity is. I'm very well positioned in understanding all of the beauty of Einstein's theory of general relativity, and you really need to embrace that to being able to make the small little tweak to it.
I guess, and maybe this is an unanswerable question, but I am interested in that moment when you realize that maybe something that is taken as a given is so much not a given for you that it's actually worth giving up and pushing against the grain to come up with something new.
Yeah, so I think it took me really a long time, because in coming up with those ideas, we had some models, but then everything that was given, I had to some level just taking it for granted, and I was trying for years, in fact, to understand how it made sense with the common wiseness, because it simply didn't match. And I never woke up one morning and thought, oh, I'm just going to be controversial. That's not at all the way I was going about it. It just wasn't working out. And for me, it was very much taken into, there must be something wrong that I'm doing, and I was keep going to it again and again and again for years. I was redoing the same thing, not understanding how it was connecting with what we knew from the common knowledge had to be true. Until, in the end, it was simply there as a mathematical fact that some equation did not match out. And when you see that things don't match out, then you have to go deeper in that and understand the origin of that. And I was sure that it was coming from me having made a mistake, until I realized that the mistake is not necessarily always on your part.
Yeah. So take us to the moment, if you don't mind, when the puzzle all came together. The moment when you knew that your theory worked, at least to your satisfaction.
Yes, so it was over some years where different pieces of the puzzle came in, but I think there was one moment where my would-be husband at the time, and I would like to think we would still have been married even even this hadn't worked out. I was working in that model with Gregory Gabadazzi, and it wasn't quite working out, and my Andrew Tolley was in a coffee shop in Geneva at the time, And I cycled to him, and I was very excited, showing him what we were working on and what he wasn't working. And he just waited there for a second, and he started thinking about a different way to think about it from extra dimension. And we started talking about that. And it was very much the realization that some of the beauty that is present in Einstein's theory of relativity itself, when you think of it more from a higher dimensional perspective, actually that structure is fundamental for thinking about a theory of gravity. It was that click there that made us realize there is actually some beauty in it that we can explore, that we can use those as fundamental bricks for what we want to do, as opposed to have complete chaos in there. And I was just about to leave, actually, to give a talk in Paris from Geneva. So it was before we had all the mobile phones, etc. I was locked on the train, and then I started calculating all of those things. And by the time I got in Geneva, I actually had all of this to 20 order, and it was working out. It was for the first time. You put things together, and they just sort of magically work out. It's pages and pages of calculations, and it's very easy to make a mistake. But when things just cancel out beautifully and the result just match out, you know there must be something correct there. There must be something that is beyond you.
What's that moment like?
Oh, it was really exciting. It was, yeah. It doesn't happen very often, really. Yeah. So you really have to savor those moments. Yeah.
Absolutely.
Yeah.
Did you keep those calculations?
I think there must be somewhere. Yeah. Yeah.
Throughout the book, you write about falling and also failing, and you make it clear that failing isn't failure, and that it's actually a natural part of the scientific process. Could you speak to just how much of what you've been doing, and science in general, it really is about daring to be wrong?
I think that is present every day in my life, and I think in the life of all the researchers, particularly in theoretical physics, where we are exploring, and we have to challenge some of the ideas. We have to explore what happens if. And probably what will happen is that it won't work out. But you won't know that it won't work out until you try it. And it's not so much about understanding what the answer is. It's very much, I think, almost a way to organize your thought, a way to analyze all of this and give you a clearer picture on how to relate everything together. So from every failure, I think I make new connections. I learn a lot. I learn much more from all of those failures than any moment where things actually worked out.
Mm-hmm. So how much would you give credit to just an ability to be resilient and to pick up from a failure? How important is that in the
It's essential. Yeah. It really is essential. And it's not necessarily pleasant, but if you know that it is essential, and if you know that this is part of the process, hopefully it's a bit easier. I think it's not only the failure in itself, it's also how you represent this failure with respect to others. I think there's a lot of expressing that, and there's a lot of the time where, because of those failures, you may have the impression that your position in the field or your ability to drive new results is not as important as someone else in the field. And I think it is very important to bring those aspects to life and to very much realize that we are making progress together. I think that can be very daunting, particularly if you start in the field and you have the impression that there's all of those successes out there and you are the only one attempting and not necessarily succeeding at every step.
So can we infer from that you'd be at peace with the idea that your theory may sometime be proven wrong?
Oh, it most likely will, and that's okay. That's okay. That's not why we go through it. Yeah.
A quick question about something you've made reference to a few times in your book is that despite the fact that there is an increasing number of women doing what you do, and in very prominent positions, and indeed at this very institution, at some stages in your career, you have found it difficult to show others that yes, women could do what men can do. Could you speak to how that affected the way you worked? Did it make you more determined to prove that what you were trying to achieve is actually doable?
So I would say yes, but after quite a lot of level of resilience. And I think this threshold you have to go through is quite detrimental. I think there were many times throughout my career where it was simply too much. It's not that there's resistance against women per se, it's this notion that there's one way to be a scientist, and if you are not following that mold, then that's not the right way to being a scientist or being a theoretical physicist. And I don't think anyone per se thinks like that, but it is a little bit of, you may have this impression when you go through it, and also when you have to go through day after day, finding the own motivation within yourself and finding it hard to get recognition from the outside. Recognition from the outside is very, very hard to gain for anyone, for anyone at all. And so if you may not look completely the same as everybody else, sometimes it gets a little bit harder. I think after a while, you can step back a little bit and think, well, actually, let me go through it and let me take that on, and I'll show them to some extent. You can do that. You can do that for a year. You can do that for several years. It does get to it to some extent as well, and I do know that for myself, and I do know that from a lot of my colleagues. After a while, you may also wonder why you need to keep doing that when it does take a lot of your energy to keep having this level of resilience.
Yeah. Last couple of questions. You write in your book that the majority of the scientific community was skeptical about your theory. What's it been like dealing with whatever challenges have been sent your way regarding the theory?
So, yeah, that's interesting. In retrospect, I can say, well, I knew mathematically it was correct. I knew also all the arguments that were thrown in my face, actually, hadn't necessarily been quite as thoroughly thought through than what I had thought through, what I had gone through. So there was this level of scientific process that I could stand on and think, logically, I know this I can actually rely on. But you have to separate that from the human process in being in a room full of people that tell you, you are wrong. and you can stand up and say, well, actually, look at this. But it does require quite a lot of motivation there as well. I think in retrospect, I can say, yes, it made me stronger to some level. And some of it, I think it is true, is necessary in the scientific process, that we don't just take everything for granted. We can't do that. We have to go through some of those levels. But perhaps sometimes it could have been done, maybe in a more positive way for everybody.
Yeah. Even if your theory is proven correct, is there a way for us to know what we don't know? How much do we still need to know?
Oh, I think this is one of the beauty with Einstein's theory of relativity, that we know for sure we don't know. In a regime where the theory that I've been working on, and I work on other things, but that theory there will have nothing to say with what happens at the center of black holes, for instance, and in a regime where gravity becomes so intense that we can't use the Einstein theory of relativity to describe it. So we are very lucky in that respect, that we already know what we don't know. There may be cases where we actually don't know how little we know. And the more we discover, the more we understand, we realize there's so much more to uncover. Sometimes you actually need simply to wait for experiment and observation to really show you what it is you thought you knew, but actually you don't know. And so it is very important to rely on all of this exploration of the real world to confront it with what we have. But there will come a point where things become so intense and almost so abstract that it is indeed hard to understand how little we know. Yeah.
What are you working on next?
So what I work at, I work on different things at the moment. One of the things I'm quite interested in is not in the behavior of gravity on the large cosmological scales, as I described there, but much more to understand how to make connection between gravity or reality in a regime where we don't have access to experimentally or observationally, and we won't have access to it in the next thousands of years. It's simply not going to happen. But still, consistency of reality in that regime has implications in our everyday life and has implication in observation and experiments that we have access to now or in the future, and making that connection much more concrete. To me, that's exciting because it's almost having a window of opportunity into the unknown.
Yeah. And actually that plays really beautifully into my last question, which is, this has been your life's work and will continue to be your life's work. But for the rest of us who don't maybe understand the intricacies of what you're doing, why does it matter? What is the big picture here? Why does it matter for us to know all of this?
I think the reality is that that's what makes us who we are. I can tell you it matters. Some of the things that were discovered 100 years ago, some of the things that were discovered 20 years ago, they do matter because we are using them in our technologies. We actually matter for everyday life. They do concretely matter for everyday life. But I don't think we are bigger than that. That's not why we do it. We don't do it directly for the technological application of tomorrow or in 100 years. We do it because we have to keep searching. That's who we are as humans. That's the beauty of what we do, how we do it. And so we are all driven, I think it is true, we are all driven to the most fundamental question of what is our origin, what is reality, and we need to keep exploring that. I think it will never stop.
I hope you never stop. Thank you so much for taking my questions.
Thank you.
Really appreciate it.
Thank you.
So great.
Thank you.
Thank you. Thank you so much, Claudia. Thank you, Nahlah. All right, so now we have time for questions from the audience. So we have a microphone that's set up on the stairs over here. So if you have a question, please make your way to the microphone. As we have people standing up for questions, I will kick us off, and we'll get a queue going up there. I guess maybe I just had a quick question for you. You mentioned the graviton, and this particle nature of gravity. And in what way would the graviton help us reconcile gravity with the other forces and with quantum, quantum physics?
Yeah, that's a very good question on what is the place of the graviton in the unification of gravity with the other forces of nature. And I think the question is driven by a lot of work here at the Permata Institute and throughout the planet, actually, is in trying to understand unification of gravity with the other forces of nature. Actually, in our regime, we know very well how to think of gravity at the same footing as the other fundamental forces of nature, and thinking of a particle, the graviton, being a representation of the phenomena of gravity, just like the photon is that for electromagnetism and the other fundamental particle. I think your question is how much this notion of graviton itself is important when we want to have a fundamental theory unifying gravity at a very high energy regime or in very highly curved environment. And then I think then, for instance, one of the beauty of string theory, which is one of the potential candidates for a full theory of quantum gravity, is that it does predict in its spectrum of reality the existence of a graviton. Naturally, the graviton emerges from this picture together with other fundamental particles. So I think in any fundamental theory of quantum gravity, we would need to be able to see how this picture emerges. And having the picture of the graviton emerging is very important. At the particle level, is actually not so very different from a photon per se. They are both massless particles. Well, the only small difference between the graviton and the photon is what we call the spin of the particle. That's a representation of the particle, which is related to how it transforms under rotations in space and time, but under rotations. And so we say that the photon is a spin 1, it has a particular type of symmetry, of representation, and the graviton is a particle of spin 2. That seems like a very small difference. At spin 1, for instance, if you make a rotation, you can rotate it by 360 degrees, and it comes back to the same thing. For a spin 2, you can think of something like that, and you can rotate it by 180 degrees, and it comes back to the same thing. That really is rotation in space-time, but if you want to do the analogy. So in that level, it doesn't seem so very different, but we know that has implication for how we think of interactions with gravity, which are really, really fundamental, and has affect the behavior at very high energy to the point where we know we need something more than just that particle when we want to think of it at a fundamental level.
Cool. Perfect, thank you. All right, so we have some questions from the audience. Go ahead.
Thank you for the talk. You spoke about building a model of the universe where the force of gravity would drop off after long time and distance. It might be strange to think about gravitons as something that could decay, but if they could decay, but they were otherwise very stable and had a very high half-life, would that do it? Would that give us that sort of drop-off, but over very long distance?
That's right. And actually, this is very much embedded in those ideas. So if you want to think exactly as a theory of gravity which switches off to some extent, what it would mean at the particle level is that the graviton itself has a mass, and therefore it can indeed decay. The lifetime of the graviton is associated with its mass, and because it has a very small mass, in units that we're used to, this is a notion of energy or mass is inversely proportional to that of distance or time. And so the lifetime of the graviton would be related to the size or to the age of the universe itself, because that's when we would like this switch off to occur. So it would be a very long timeline. But in principle, yes, absolutely, that's one way to think of it.
Thank you.
So when you were talking about the number of orders of magnitude that the timeline was off, or rather the speed was off, the thing that struck me is that sounded like the ultraviolet catastrophe that led to the development of quantum theory, and I thought you were going to say you've solved how to quantize gravity, and then you went down this. No, that wasn't it. It was, does gravity have a range, not infinite? So 2 parts to the question. One is, given that analogy in my mind of where you were going, you didn't see that. You saw going to range and saying, well, does it have a finite range and not an infinite range? And how do you determine what that infinite range should be, given what we know? Like, I didn't see how you got there, and I didn't hear you talk about what that range would be.
Okay, so I can answer the last question first, and then for the rest, there's a lot of things going on, so I can try to go through them. The range of gravity that we would want to, that we would need is actually comparable, maybe just a little bit smaller, but comparable to the size of the observable universe today. And so that corresponds to a mass for the graviton, if you want to think of it in these terms, comparable to actually the amount of dark energy, if it would be, of the universe today. So it would be, if you want to be very precise, of the order of 10 to the minus 32 electron volts. And that is for different reasons, because beyond that we also need to explain the acceleration of the universe, but also we know we have very strong evidence for the behavior of gravity up to very large distances. So we can't have the range of gravity switching off too early. So it would be comparable to the observable universe today. Now, related to the ultraviolet catastrophe and some of those effects, there are some level in which they are related. Perhaps what you think about in the vacuum is some level in which some of the quantities that we predict would seem to be infinite in themselves. In reality, they're not infinite. It's just that there's possibly some new physics that come in that switches some of those effects off. And this I will remain relatively agnostic about. I don't know whether there's new physics that goes on beyond the standard model of particle physics that I know of. The only thing, so I'm not going to account for any of this ultraviolet catastrophe. The only thing that I know for sure is that we have detected, for instance, the Higgs boson. Well, I know that there are some particles out there which constitute the particle of the standard model, the Higgs boson, the top quarks, etc. Those particles have a mass. And so I can, just from those particles themselves, consider the effect that their quantum fluctuations would have on the vacuum. And I'm not considering anything beyond that. When you're thinking about these type of questions, you are sometimes being faced with a much more bigger discrepancy. You may have heard of a discrepancy of 120 orders of magnitude discrepancy of the cosmological constant problem, which is sometimes called like that, between our expectations from the vacuum energy and the observations. This 120 orders of magnitude discrepancy is coming from the expectation that there may be some physics out there, some particles beyond the standard model of particle physics, all the way up to the Planck scale that also contribute to the vacuum energy. That I don't know anything about, so I'm not going to consider them at all.
Okay, thank you.
I'm sorry in advance if my question is too elementary. When you use the analogy of light to explain gravity, does gravity also exhibit the wave-particle duality nature? And if so, what are the ways in which we can play with gravity just like how we do with light?
Yes, excellent. So I don't know if everybody has heard the question. Let me just rephrase your question, but it's an excellent question. In comparing gravity with electromagnetism, is that the way you said it? If gravity also exhibits the same particle wave duality as electromagnetism or as light, and if so, how can we detect those? These are amazing questions. I wish I could just answer you. This is the way you would detect it. So yes, absolutely. When you think of light as exhibiting a wave-particle duality, we can think of light as electromagnetic waves that travel through space and time, but also at the fundamental level, we have evidence, we have detected the fact that gravity is made out of finite quanta of energy, which can be thought as particles, and that is the photon. So light sometimes has a wave-like behavior, and sometimes has a particle-like behavior. Now for gravity, the analog of light is gravitational waves, what I like to call Glight, but it doesn't matter the name. And so definitely for gravity, we have strong evidence of this wave-like behavior for gravity. Well, we don't have interference with gravitational waves, maybe not yet, but we do think very much that gravity can exhibit some wave-like behavior. Now, to see if there's a particle wave duality for gravity, we would need to be able to detect the particle within gravity. And that's going to be really very, very challenging. Maybe not impossible, really very challenging. And I'm a theorist, so. But the gravitational waves that we have observed, not me, but that people have observed, we can think of them as being made out of gravitons. They would be made out of roughly 10 to the 44 gravitons. And so, as humanity, it took us 100 years to set up the technologies so as to being able to detect those gravitational waves. And when they reached us here on Earth, they managed to stretch the distance between two mirrors in interferometers, which are located roughly 4 kilometers apart. They distort the distance by something which is less than the size of a proton. 10 to the 44 gravitons working together, team working together, they managed to change that distance by that amount. So if you want to see the effect of just one single graviton, you need an experiment which is 10 to the 44 times more sensitive. But that is not just technologically challenging. It's theoretically impossible to have that, because then you go into Heisenberg uncertainty principle, where you're not even able to measure to those distance scales. So you know that to actually detect single gravitons, it would be extremely challenging. You can hopefully prove the quantum nature of gravity in different ways, maybe by proving the statistics of quantum fluctuations at the beginning of the universe, but detecting single gravitons is going to be really challenging. Maybe you can come up with a way to do it.
Thank you so much.
You mentioned using quantum fluctuations and general relativity to explain the expanding universe. Quantum mechanics and general relativity are two theories that do not always get along. So I was wondering how straightforward it is to use concepts from both theories, and if you need to account for the differences between the theories in doing so.
Okay, so that's an excellent question, and also related into how we can come up with a grand unified theory of everything that includes gravity in all of the quantum framework. So when we think about the challenges in unifying gravity with the quantum realm and how challenging it is to do that, what actually happens is this is what happens at very high energy scales, actually, at very high curvature scales. But when we're thinking at much smaller energy scales, there's actually not such a big controversy as what we would want to say in combining gravity with the quantum realm. And actually, we do have a quantum effective theory of gravity. We can't think of graviton. We can't do that. And this is not controversial per se. So thinking of gravity and embedding it in a quantum framework in itself, that is not the challenge per se. And thinking of quantum field, living in a gravitational setup, that is not challenging per se. I'm not saying it's completely right the way we do it, but actually we do that. We have the techniques, we have the tools, we think we do that relatively well. In fact, when we do cosmology, what we do observe, for instance, if you think of the statistics that we observe in the temperature fluctuations in the cosmic microwave background, those temperature fluctuations, they're completely consistent with quantum fluctuations that happen at the very beginning of the universe. And so we are thinking of quantum fields living at the very beginning of the universe, having some quantum fluctuation, affecting the very structure of the space-time. We can look at how these have evolved with gravity throughout the ages of the universe, have implications that are observable today, and this is completely consistent with our expectations. So this quantum framework of the field living in space-time and gravity itself, and even thinking of gravity as having some quantum fluctuations, that in itself is not so challenging.
Thank you.
All right, I think we have time for a couple more questions.
Hi, I thought it was really lovely when you mentioned that it's really great to recognize a theory's limitations because it gives an area for further exploration. I just wanted to ask what part of the theory you've developed with your colleagues that you're most excited to be expanded on next?
That's an interesting question. I think in deriving it, what I was the most excited with was to come up with a mathematical architecture in some sense, coming with some inner beauty to it that was consistent in itself. That is very theoretical to some extent, and it may not be the answer you're looking for because the connection between that and reality and observations may not be very tangible, and maybe there isn't per se, but in terms of this inner beauty in itself, in how things can work by themselves and be intermingled in a way that is consistent, that does make sense, that to me was very exciting.
All right, thank you very much.
Thank you.
All right, I think we have time for one more question from the audience.
You talked about gravity affecting everything universally, consistently, and also it's attractive. Is it theoretically possible to have other forces that affect everything consistently, or different strengths, or repulsive?
So to have another phenomenon, another force out there, which would be universal in the same way as gravity would be. I think if you want, it's almost the way Einstein came to it in the first place, of this notion of equivalence principle, this notion of universality led to the very notion of gravity through space-time itself. And so I think if you wanted the same type of universality for another phenomenon, you would be driven to the same type of conclusions.
That just cancel each other out, kind of?
Or you wanted to act in the other way, in the opposite direction. Yeah, that is very challenging to do for stability reasons. Yeah.
Thanks.
Thank you.
Okay, thank you so much to our audience for those excellent questions. We will conclude. Before we thank our speakers, we just want to let you know that there is a book draw tonight. The prize is a signed copy of Claudia's book. One lucky person has a postcard taped to the bottom of their seat, and if you have the postcard, come see Evan afterwards. Before you all go look, please let us take a moment to thank our speakers, Claudia de Rham and Nahlah Ayed.
Congratulations. Great.